literally mean everyone. So not only academics or people that know how to work with Earth observation or AI, but everyone with a spatial question. I'm CEO of Spheer. We started Spheer together with these two people, with Mark Boer and Dominique Cirkel, 4 years ago. But we bootstrapped ourselves. So at first we did all kind of contracting and consultancy on different AI projects, also biotech projects. 2 years ago, we properly started building Carto, but we have had experience with training machine learning models on satellite data from just after Sentinel-2 was launched. So we did our first Sentinel-2 based machine learning project in the Netherlands in 2017. So we have quite some experience there. But we don't do it alone. We have a larger team around us. Some are building the web platform and thinking about the user experience. Others are making sure that the backend scales so that we can not only serve local maps, but also, if we have good working models, zoom them out to maybe the whole of the Netherlands, for example. We have a university collaboration with TU Delft. So this is the Joris Timmermans from TU Delft. We have a collaboration there already. And many more. So AI engineers, every one you need to serve clients, let's say. In the coming hour, I want to talk about, I first want to start with why GeoAI, because there's plenty of different ways to look at geodata. So why are we using AI, and what do we consider GeoAI, and where is it going? Where do we anticipate it going? We'll talk about what kind of data we use, because the data space is getting ever larger. We're starting niche, planning to go abroad that, but we have a kind of specialty. Then to go on to machine learning on geodata. I discussed with Serkan, and I'm assuming a low level of experience with machine learning. So probably half of you has a lot of experience with machine learning, but bear with me. I want to start at the basics, and I won't go too deep into technicalities there. And then I will discuss what's the problem with conventional machine learning and why are foundation models so great. What do they bring to the table, and how do you train them? Where do you start? What's different than what we did before? Then to go to the results of our model. I adopted Spheer foundation model just yesterday. We haven't given it a name before because we don't publish, so we didn't have to. We just call it our Geospatial foundation model. But I thought the Spheer foundation model would sound okay. That will be the most technical or the most scientific part of the talk, I think. And then I'll go on to Carto, the actual app we built around our foundation model. Very shortly about the tech stack that we use, just so if you're interested, I can connect you with my CTO. I'll try to give a live demo, which is also always exciting. We'll see if it works. And then discuss some use cases that are actually already being solved and monitored or have been monitored the last year. And then to end up with what's next for us. And hopefully I'm done in an hour. We'll see. So our motivation, just as I think yours and the motivation for many people to work with geospatial data, is that we feel that Earth observation is crucial and central to solving many global problems that we have. And I only listed a few here. There's many more. There's urban problems. There's defense, of course, but those are not so much our niche. But if you look at what everyone suffers from on the globe, it's food security, water quality, pressures of rising tourism on ecosystems, but also on infrastructure. But on the right side, there's the topics that we have the most track record on. That's biodiversity, so ecosystems, climate adaptation. Are we prepared for rising sea levels? Are we prepared for a lot of water going through rivers, etc.? And behind these simple icons, there are, of course, hundreds and hundreds, maybe thousands of different questions and use cases and maps people want to see. And to use our Earth observations to create those insights, to answer those questions, you can basically take two approaches. And I'm going to paint a very black and white picture, of course, and there's a lot of gray area, but just for the sake of my story, I'll make it very black and white. Roughly, you can take the approach of physical models or machine learning, where physical models are well thought through, human-engineered models based, of course, on scientific data, on tests, etc., and on physical models of the world, where the patterns you look for in Earth observation data are determined by human experts. Right? They are human-engineered. You need a deep understanding of the physics. But if you're able to create a physical model, then all the assumptions that you put in there make it very explainable, right? So if you get something out, you can very well explain where that answer, that insight came from. The models are typically very use case specific, so you can create a physical model for one type of insight you want to get out of geodata, but that doesn't port to other questions. You have to start all over again. And that way it's not scalable, it's static. You have designed it and then you get information through and you look at it, right? It's not adaptable to interaction with humans. While on the other side, we have machine learning, statistical models that start very dumb, but are able to fit very complex functions. And they don't do it by asking human experts, hey, what function should I fit? But rather, they look at high quality examples. They need a lot of trained data, and they combine that trained data with the Earth observation data, and they look for patterns that correlate between the two, right? And the more data you have, the more elaborate these models can become, and the more accurate they can become. The catch is that because you leave the pattern recognition to a statistical model, by definition, you're letting go of explainability. Right, that's a big topic in machine learning, and it's a given. So you have to look much more for rigorous testing, validation of your model, and what are the edge cases, etc. So you have to be careful there. But on the pro side, in principle, these statistical models, I mean, they have different kinds of architectures, but within one architecture, you have made a generic approach. So you can use kind of the same approach to many different questions. You can take one question, train a model. You can take another question with a related label data set and train it again. So it's more scalable in that sense than physical models. And you can make it active. And by active, I mean that you can have it serve information to users, ask for feedback, and take that feedback into account and retrain the model. So that if you think if you design it well enough, you can make an iterative approach to getting information out of data. And because of the last 2 points, specifically the scalability, we have specialized in GeoAI. That doesn't mean that GeoAI will take over all modeling, because there's a lot to gain from physical models. So that's never my story. The story is that there's a lot of room to expand, a lot of questions to figure out, and GeoAI can play a very important role there, also economically. Because who of you, and I cannot ask the people online, but who of you here in the audience have heard about long-tail economics? Okay, it's an interesting aspect of the modern age, of the internet age, and if I get the definition of Wikipedia, it says that long-tail economy is about the type of items that you can only sell to a couple of people. So there's not a big market, but if you can make the costs to do so low enough, then there's suddenly a feasible market. So if you look, for example, at the music industry, what internet did for music and video and all kind of niche entertainment markets, suddenly they became feasible. You didn't need a physical store room to sell video content or music content. So suddenly it was worth it to make a new album that only 10,000 people buy it, right? And if you make the costs low enough, there's suddenly a whole economy that people didn't anticipate. So I'm convinced that the same is true now for Earth observation, that we're in a regime where only use cases that are where there's so much money involved that they become feasible are now being built. While we might have hundreds, maybe thousands of questions that we want to ask about the spatial world that we now don't do because it's simply not feasible. And why is it not feasible? Because creating satellite monitoring is cumbersome, as you know. I mean, you have a whole institute focusing on it, right? And you're not the only one in the Netherlands alone. So it requires teams of specialized people about the data side, about the infrastructure side. You have modeling experts either on the physical model side or the AI model side. And it easily takes weeks or months or even years to develop a use case based on satellite data or other geodata. And we believe that GeoAI will do two things. It will make the head more efficient, and the head is I mean the part of the market that is already being served. So modeling will become better with the help of GeoAI and just cheaper. But more importantly, it will open up a tail for way more custom satellite monitoring. So almost where you will have a question and you sit down with the AI and talk it through, like we do now with ChatGPT for a lot of, for example, legal questions or language-related questions. On the bottom right, there's a screenshot from the USPA market report. So the USPA is the agency for the space program of the EU, not to be confused with ESA, which you very well know. So USPA is only a couple of years old, but they make a very nice market report. And if you look at the bottom left figure, so that's roughly 3 billion. That's right now, they estimate that that's the current market for value-added services. So not the data itself, not launching satellites, not the operation of getting data out of space, but everything that gets after that, right? So turning that data into value for whomever. That market is now globally 3 billion. They estimate it to grow to roughly 5 billion in 2023. But I'm fairly sure that they are not taking into account what GeoAI will do. And I'm convinced that this figure will grow a lot bigger. And that's exactly for that tail that will open up. And if you bear with me, I have a future vision, let's say, and of course, we can experience all kinds of blocks there. But just to go a bit sci-fi, I think it might be conceivable that in 5 to 10 years, we'll see the same happening in the physical space as we've seen in like the language space. And we'll end up, or at least move towards a situation where we'll have spatial advisors on demand that understand the physical realm and can discuss with human experts and complement them. And complement in a way because they can look at very large data sets while the human cannot. They can look at patterns that are not human intuitive. They can look back in time, and humans can use that data to work faster and get a more comprehensive picture of spatial problems. There's roughly 2 requirements there, and we work on both. We'll need artificial intelligence that understands the physical world, much like GPT, like the engine in ChatGPT understands the textual world, right? It's a very different space. It's a very different data set to understand. And once we have that, we need intuitive and fast interaction between humans and that AI. And I'm convinced that the only way to get that really working is to have it at human thinking speed. That's what ChatGPT did for language models. Before that, it was academically mostly. And they brought the speed up so far up that suddenly everyone could converse with AI and start to get an intuition for what it can do. So that's our motivation to work in the GeoAI space. We have a bit of a niche experience, and that's on satellite time series. So from the first time we worked with satellite data, we started to look at temporal patterns rather than spatial patterns. And a very nice data set, of course, to do that with is Sentinel-2. So we have done, we've worked with aerial photos, Sentinel-1 a bit, but the core of our business is always Sentinel-2. And this is a little data set downsampled, otherwise it wouldn't fit in PowerPoint, but of the north of the Netherlands where we monitor the salt marshes. And as you see, it's very rich. The temporal part is, there's a lot of data. In principle, Sentinel-2 flies over every couple of days or, right? So if you collect it, you literally have a video of the year, the whole year. And of course, there's a lot of noise in there, but we deal with that so that we end up with nice temporal patterns. And it's not only temporal, it's also spectrally very rich. So if you look at the x-axis here, there's the wavelength of light. On the left, on the bottom left, you see the more or less the human spectrum that we can see, red, green, blue. And Sentinel-2 sees a lot more. So it sees a lot of, it also sees UV, and it sees at 20 millimeter resolution a lot of near infrared and very narrow infrared bands. So, and those have very interesting information about the vegetation. The title of my slide is 10 spectral bands at 10 meter resolution. That's of course a lie because Sentinel-2 doesn't provide them. But we simply take the 20 meter bands and we downsample them, I think by very simple interpolation, maybe nearest neighbor or cubic interpolation or something. And then we end up with a data set where we have 10 bands at 10 meter of principle the whole Earth. And what we do then is look at the spectral-temporal patterns rather than the spatial patterns. We have worked with spatial patterns in Sentinel-2 as well, but we found out that for the majority of applications, there is no information at all there. There's just not enough spatial detail. So we tend to throw it all away. We cut all the pixels loose. I didn't have a video of just one pixel, but focus on the middle one and you will see exactly the same thing that our model sees, right? It's a single 10 bands color that changes over time. That's basically the information we train models on. So while people think we do computer vision, it's much more time series analysis. And on the label side, typically what we do is, you have to match examples of what's happening on the ground with your satellite pixels. And those examples are typically vectors. So we rasterize those labels and we have different flavors there, but usually we only keep the pixels that are fully in a label factor. So in this part, you could imagine a regression model that we like to train of some phenomenon, and there's a shape where there's 30% of that phenomenon and 70% of that phenomenon outside. So we only use the label pixels that are fully inside that shape. So we are very sure that the Sentinel pixel represents this phenomenon, and the rest we just put on NaN. We throw it away, like a very gray area on the right. And if you want to train models with that, it's quite straightforward. Putting aside all the details as architecture, model architecture, and the actual loss function, etc., it's behind, under the hood, it's all the same. You take satellite data you first ask someone who knows the problem very well. So here's a real case that we're working on, but it's virtual data. So herb richness of grasslands. You ask some expert, hey, can you tell me where there was herb rich land and where there was herb poor production grasslands? And they'll come up with these polygons, and you have to ask them, so at what time did this apply? And then for those areas of land, we collect the Sentinel-2 time series, and we are able to take those examples and train a statistical model. And you can test whether it works because you hold back part of the data, you hold back a test set. And if the model is able to find patterns that correlate between the two, at some point it's trained, and you can use it for other pieces of ground, for the yellow pieces, of course, and ask them, hey, given these satellite time series, what do you think about the herb richness? Basically, that's it. So that works, but there's a catch. And the catch is that it's really slow and expensive to do this still. Also with AI, because every use case requires many examples, so you have to collect many labels, and usually there's weeks to months involved there. That's the outcry for every machine learning project is we need more labels, right? It's the most common heard thing in AI. It can take months to develop by specialized teams, and this is exactly what we did until 2 years ago. We did cumbersome projects where we took months to collect data, clean it up, and train these models, verify that they work. And it's a pity. So we started to think, how can we do this differently? And then we saw the rise of language models. We did some consultancy on biotech that also used foundation models. And so we got a vibe we got knowledge about how are these models trained. And we thought, how can we take this knowledge and project it on satellite time series? So make a model that understands satellite time series. Because if you want to take the old approach, the conventional approach, and try to serve that long tail economy, you cannot do it, because every time you have to start over. So we started to work on geospatial foundation models to make GeoAI that is fast and interactive. And the way it basically works is you first train a model, a foundation model, that doesn't need human labeling. That's basically the catch. Foundation models, whether they be geospatial or language or whatever, you have to figure out a way where it can train on the input data itself without giving it, telling it what it's looking at. So no label data involved. And after you've done that, you have typically those are very deep neural nets. And they do most of the processing, and they turn the raw input data into something at the semantic level, where all the noise has been removed, all the unnecessary details have been removed, and they sort of summarize the data set to the point where you can train a very simple model on it. And there you need labels again. But because the foundation model has done the most of the processing, you hope that you only need like a tiny amount of label data to do the last pushing towards a certain use case. So that's the philosophy behind it. Make something case agnostic so that then you can use it with a very small label data set to train. So again, we train a geospatial foundation model. It's a deep model, no label data, and that means that you are basically able to use all satellite data. Where before we could only use satellite data where we knew something about the use case we want to train for. Now we are not limited by that. We can use basically the whole world. We're only limited by infrastructure, not by label data. And this is still a bit uncertain, but the philosophy is that if you train such a foundation model once, it takes a lot of CO2, takes a lot of compute, but then afterwards you get it back because the specific use cases only use very tiny models and you don't spend the CO2 there. So people anticipate that it will also have influence on the amount of energy that is needed for AI. And so the training of that use case model that learns to turn the insights of the foundation model into a specific use case, that's called fine tuning. It's typically a very simple model, and when we set out, we hope to reach 2 orders of magnitude reduction in both the necessary labels and the train speed. So to talk a bit about self-supervised learning. So the creation of a foundation model is almost always done by self-supervised learning. So what I showed you before is supervised learning. You have a statistical model, and the supervision is basically the part where you insert the input data and you tell it, hey, you should end up with this answer. And if you don't, I'm going to punish you. And if you do, then I'm going to reward you, right? That's the supervised process. And to have a model learn patterns in your data set, you have to do something similar, but come up with a smart trick. And I always find the way how large language models are trained very insightful. They typically do this by something called reconstruction. And this is the way they do it. So you collect a lot of textual data, and then you ask the model, hey, I'm going to put my hands on part of that data, basically 10 to 20% typically, and ask it, hey, can you fill this in? Based on the surroundings, on the surrounding data, can you fill this in? And in this case, I think you will be able to do it, right? So what's under here, under the first hand? Rule the world. What's under the second one? Sure. Someone is mad at me, I think, because I like cats better than dogs. But... sorry. Could be right or better, or that it could also be worse, although that doesn't make sense with the first sentence. But this basically. Participants? I think you can do mute basically. Unmute you is also this account. Okay, yeah, but I can unmute myself maybe.
You are muted, Jacob.
Am I back?
Yes, you are.
Okay. Yeah, let's go again. Okay. So we saw that if you force a model to fill in those gaps, it has to learn language, and that's exactly what large language models do. On very large data sets, they have to fill in the gaps, and then they learn language. So we can do the same with satellite images. Actually, we can take an image, we can mask out part of that image, force an AI model, a foundation model, to fill in that gap, and it has to do something. And we can calculate the difference between what it has filled in based on the surroundings and the actual image, and make that a loss function and optimize that loss function. So we compare that, we update the model and keep doing that. And this sort of works. But can you think why this wouldn't work as well with Earth observation data as for text? Yeah.
The software is a thing that you are trying to predict is unpredictable. Patterns created by humans.
Yeah.
It's not an interpolation case where there's some physical reason for those things to be really in the middle of the whole thing.
Yes, exactly. So to frame that differently, the fundamental reason why this is different than language is because language is at a much a very different abstract level. There's already a lot of condensation of information. Let's say we made up language to communicate abstract ideas. And there's a high level of correlation between them, as you saw, right? So there's a high level of correlation between these words, and that's why the reason why if you take one away, you can easily fill it in, right? There's all kind of subtle or less subtle connections between those words. While in the physical world, there's a lot of noise. And if you mask out part of the physical world, it might be maybe impossible to fill it in based on the surroundings. So you have to, and this is exactly what people do, and they did, and they made geospatial foundation models. It's very finicky. You have to mask out maybe a bit less or a bit more or vary a lot, but it's very human engineered. It's not robust. It's finicky to get well. So we thought of something different, which I'm not going to explain because it's our trade secret. I am going to refer you to a party that does it somewhat similar. But basically, this is not what we're doing. It's until basically 2 years ago, people were taking this approach. it's not the way to go. So lesson learned is don't do reconstruction on physical world data. If we look at what has been done in the field of geospatial foundation models, then it started more or less with Presto a couple of years ago, and Clay. Clay works more like a computer vision algorithm. It looks at a lot of spatial information and not really at time series. We launched our first successful model in March previous year, so 1.5 years ago. And after that, a couple of more models have come up. For example, Google Alpha Earth. And I'm going to show a comparison between us and the last two, because Google Alpha Earth still took basically the reconstruction approach mostly. So that's the core of their approach. While Cambridge, Tessera, they take a very different approach. So if you're curious how to do it better, then have a look at their paper. They do it way smarter than Google does. So it's a vibrant field. There's a lot going on, and we try to compete there, do something smart that's competitive, at least for nature monitoring, for agriculture monitoring, and water monitoring, and many more. Our model was trained on only on the Netherlands and only on parts with major areas right now, and it was trained on satellite videos of a calendar year. So basically, this I can tell you, we take time series of exactly a year, calendar year. So we cut off a time series of a pixel, and we take each time series through the trained model, and it will give us embeddings. So embeddings might be confusing, but it's actually a confusing concept, but it's actually very simple. It's a set of numbers. It's a vector, right, with numbers, and that numbers should have a high information content. It's not human readable, right? It's abstract, but it's very high level of semantics there. So it's readily usable for fine tuning. And in our case, we can nicely visualize that by taking an area, get each pixel for a certain year, get it through the model, and then look at that vector and bring it back to 3 values by dimensionality reduction, for example, or just taking 3 random vectors. Or 3 random dimensions, and then you end up with a RGB picture. And here on the left side, you see an aerial photo of a salt marsh in the Netherlands, and on the right side, you see our embedding for that year. And you see spatial coherence, and that's because every type of different land, so the more you go outwards and northeast, it's going towards the Wadden Sea. So there's different land there because it overflows. And the more you go to the south, actually, you see the dike there in the bottom. So it's very different types of grounds, different types of wetness, different types of vegetation, and you see that back in the embeddings. If we of course did comparisons with Google. We were very excited when Google Alpha Earth said, "Hey, we have embeddings," because it convinced us that we took a right direction a year before. Right, that we moved in a direction early where giants are now coming, but we were also a bit afraid, right? So if Google does something, we might get out of business. So we set out to very quickly compare them. And this is a fine-tuning case where we took a label data set for a very specific use case, a certain type of grass on heathlands. And we fine-tuned with the same label data set on Google embeddings and on our embeddings. And what you can see speaks for itself, I think. Our spatial resolution is somehow way better. We see very tiny details at the 10 meter, tiny, it's the 10 meter scale, while Google's has some spatial blurring. And we tried to discuss this with them. It's not in the paper why this is, it's not immediately clear out of the paper. But we think that because they had to make something that's immediately globally applicable without any support, they had to take some shortcuts. That's what we think. We also compared with Tessera, and here I compare the raw embeddings. And don't look at the exact colors, because for both we just took 3 random parts of the embedding to visualize. But what you can see is that the Tessera embeddings have artifacts. They have artifacts on the 20 meter scale. This is really their raw data, while ours are much smoother. I have to say, I have to be honest here, that we did fine tuning here, and the fine tuning already looks a lot similar. So a lot better on their side. We think we're a bit better. We have a bit better stability throughout years. So we saw some odd things there, but it's already much closer to what we can yield as what Google did. But still, I'm convinced that also the embeddings themselves should look good. So you can overcome weird artifacts with fine-tuning label data, but you will need more label data. That's my conviction. So I'm still happy that we're doing a bit better here. Yeah, now I'll dive a bit more into quantitative results. So before we started working with our foundation model, we had two large-scale cases where we collected a lot of label data. So painstakingly, weeks, months of going through data, throwing away data that wasn't useful, validating it, etc. And one of them was Molinia cerulei. That's in Dutch pijpenstrootje. There we are. And that's an indicator of nitrogen deposition in Dutch heathlands. And since nitrogen deposition on nature is keeping our society locked, this is an interesting indicator that we started to look at. And we basically, we monitor where there's a lot here in yellow, or there's barely anything in blue, or in intermediate stage. And what we did is we compared the models that we trained before, which are the solid lines for 3 different validation areas. So these are 3 nature reserves in the Netherlands where we have label data and where we didn't train. So really, truly new data. And we compared that with what happened if we trained on the raw Sentinel-2 time series, so no foundation model, or we turned those into embeddings where we then trained the model on. And that's the dotted line. So on the y-axis, what you see is model loss in arbitrary units, but it's linear. And on the x scale, you see a logarithmic scale, and that's the amount of label data that we use. So on the right side, where you see 100, we use all the label data that we have. But at 10, we throw away 90%, right? And at 1, we throw away 99%. So it's a measure of how much label data you need to train good models. And what you see is that for basically for the supervised learning model, there was still room for improvement. You see it in the middle, the best. There's room for improvement still, so we're not trained out. While with the foundation model, you see 2 things happening, and the lesser interesting one is that you end up at a lower accuracy using the foundation model if you use all the data available for you. But the more exciting conclusion for us was that if you draw a line with from the best point of the previous model, and you compare with how much label data you need with a foundation model, there's a factor of 2 orders of magnitude. And this made us very excited. When we saw this figure, we dropped everything else that we did 2 years ago. All consultancy we stopped doing, and we focused all our effort on this, because this is basically what you need to start opening up all these other use cases, right? Largely reduce necessity for label data. So we checked other things. So this is another use case, sea couch, which is also a type of grass growing on the salt marshes, UNESCO protected World Heritage. And here temporal stability was very important because Provincie Groningen wanted to use this information to compare with their management plans. They manage there by stimulating landowners to have grazers, so cows, horses, and sheep. And they wanted to know, are we spending these millions in the right way? Should we continue doing it? Is there a statistical, a significant effect of this measure? So they needed yearly data in a very stable way. So what we did is before, now on the left side, there's the model that we did before we started using foundation models. And on the right side, there's the same, using the same labels data set, but now with embeddings. And this graph is a bit hard to read, but I'll talk you through it. On the y-axis is F1 score, higher is better. And on the x-axis is all the years that we used in training the model. So if you look on the left side, only 2017 was used for training the model. Then all the different graphs show validation on different years. Basically, if this is spread out, it means that there's no temporal stability, because if you test on 1 year, it scores high, and then on another year, it scores low, and on another year, it scores intermediately. And on the left side, you see basically the more years you put in training the model, the more years it recognizes, and the better it does on basically all the years. But each year will jump up when the year itself is included in the train data set, but it will also slightly jump up if you add other years. It's basically better able to generalize to other years, the more years the model has seen. On the right side, though, you see some difference between how it scores on years, but that's to be expected because 1 year has more clouds than the other, so there's some variance there, but the lines are very straight, and that means that already with providing 1 year of label data, it was able to accurately predict in other years. So there's a lot of temporal stability. So we saw the same effect in other studies. Here it was really pronounced because Z-Quake is not that hard. But we've seen it in many cases, this effect. So it means we have improved temporal stability using the foundation model. I'll skip this one, it needs too much explanation. And I will show you Carto. So this is a bit of a pitchy slide, so ignore the pitchiness. It's out of my pitch deck, so that's why. But basically, what I want to show you is how it looks, and you will see it in a minute. And what we wanted to realize, right? We want something that works in the browser, that you don't need to maintain yourself. You can just get into the browser and do it. You need no AI or remote sensing expertise to use it. That's very important for us. It should train a model in basically a minute, because that's, if you take longer, then people lose their train of thought. So we want to answer them while they're still thinking about the thing they're trying to train. And we want to end up with accurate maps and trends in an iterative way in maybe 30 minutes, right? So in 30 minutes, you should be able to say, is this going somewhere? And if it's going somewhere, you can put more effort, you can collect more label data, but within half an hour, we want to answer, is this feasible or not? And we were aiming for 100 times fewer examples, and I've showed you that we sort of get in that ballpark. We launched the first version of this in September last year, and since then we've been iterating. So since April, we think we have a mature version, and I'll show you how that looks. Oh, I have to change the USB. There we are. Can people at home see my browser now?
Yes.
Yeah. Okay. Right. So this is Carto. It's in the browser, right? So basically, it's a map where on the background we show an aerial photo. That aerial photo is for human convenience. It's for human orientation. It's not what the model is trained on, right? It's trained on Sentinel-2 data. And this project, or this use case, focuses on a couple of nature areas in Drenthe, so not that far away. And I'll train a model. I already initiated the model. I didn't put examples yet, to show you that I can monitor pitris, which is a very specific type of vegetation that likes wet feet. So I know this area quite well. So I know that there's pitris here. So I'll provide a bit of observations here. So I say, hey, to the model, I know that in 2024 there was pitris here, and I know that close by, this is not pitris at all. It's other grassland, and here there's more Molinia that we discussed before. So I'll put that to 0, and I'm going to train a regression model. And the first time I'm pressing train, on the backside, what happens is actually quite complicated. So we have some orchestration that's going on. We scale down compute while no one is training, and we don't have that intensive usage yet. That's maybe 2 or 3 customers are using it on a daily basis. So it might be that it's scaled up, and it might also take a while. So I'll quickly go back and talk about the tech that we use, and then go back to Carto. Yeah, people at home will see this. So The platform itself is hosted on AWS, and there was a very clear reason why we did that. And that's because AWS, from the onset of Sentinel-2, they started to keep a very nicely synchronized repository of all Sentinel-2 data. So we were able to interface with that, have our compute very close to that storage. But we run it in Europe. So we make sure that nothing of our data is happening in the US, for example. It's all happening in Europe. The front end, like the web platform, is written in React, like a JavaScript library, with Matlibre used for the viewer. The backend is written in Python. We use Fast API for the API, where the front end is asking for some computation or creation of maps or training of models. The models we use PyTorch for. Or we used to, I mean, the foundation model is trained with PyTorch, but actually the models that you train on top of the embeddings are very simple. It's scikit-learn. So probably some of you have worked with scikit-learn. It's a very simple Python library, very robust and simple AI models. The training and inferencing is done on Dask. I don't know, has anyone worked with Dask here? Okay. Yeah, so we have a Dask cluster that manages everything there. And once we have maps, they're served via a tile server, which we run in AWS Lambda. So it's very fast and responsive. If you have any questions, please feel free to contact me, and I'll bring you in contact with Mark, my CTO. Yeah, so we see that actually the server was quite warmed up. I'll show you a map. And now we have a first map based on these two simple examples of where we might find pitras. And of course, this will not be a very accurate map because we have only provided it with very local, minimal examples, but already it looks quite good. So for example, here, you see certain hotspots that you can check. So here, I know that there's indeed pitras, right? So I can either in the field or from behind my desk, because I know the area quite well, say, hey, you did this well. And I can also say, well, I think you're finding a bit too much pitras on water. I don't know if this is true, by the way, but for the sake of argument, I'm just going to say, hey, this is also not pitras. And it's now still making maps for other years, but in principle, we could now retrain. After a minute, we can take the second iteration here. That's basically how it works. Right now, we're at the stage where we can train all kinds of scikit-learn models, so ordinal classification, plain multi-class models, regression models, all kinds of stuff. And once you're done, you can export them in a standard geo format and use it in your own GIS environment, like GeoTIFFs and such. So get back here. It's if we talk about usage, it's mostly used in the Netherlands right now. We have a handful of clients, mostly governments, some companies, and terrain managers. So PBN, for example, is a terrain manager who manages the North Holland coast, the Juno area. And 7 provinces at the moment using it, testing it, how they can use it for custom monitoring. I'll give you a couple of examples. So this is a map we made with Rijkswaterstaat. They want to know the structure. They want to more or less segment the basin of the Rhine in 20 classes. And here I took the 11 most dominant classes that cover 99% of the area. And they want this for basically 2 reasons: out of ecological purposes, because they have some ecological they're responsible for the area, but also for their simulations of what happens if the water rises, right? They use this to model compared with, they have some friction coefficient for each type of land cover, and they can simulate where the water is going if there's suddenly a lot of water. And as you can see, in the first attempt, we got quite far. We're now discussing whether we're going to do something similar for the whole Rhine basin together with Swiss and France and Germany. That's still open. Structure maps of the dunes. So this is a part of the Juno area in North Holland. And here's the segmentation map, and this they're very satisfied with, especially because they want to know year after year where the open spots are, because for the biodiversity of dunes, that's actually very important to have open spots there. And one more, forest monitoring and checking of nature subsidies. So forest monitoring is done a lot. We're scarcely the first people to do this. But what we can very nicely do is discuss with them, hey, what do you consider forest? Is this considered forest? No, okay, we'll take that away and iteratively end up with something that they can use to put over their management map. So this was made for the province of Noord-Brabant. And what we found out, they said, hey, we mainly want this for the areas outside of our nature, the Natuurnetwerk Nederland. But what we figured out is that within that network, Natuurnetwerk Nederland, where they subsidize terrain managers, there was a lot of erroneous data in there. So they were subsidizing some forest as heather area, which is way more expensive. So the whole subsidy system can be updated quite easily with these kind of maps. And I'll show you only this one still to show you that we've not only worked with the Netherlands, we've done the same with the Caribbean. So we've trained an additional foundation model with Caribbean data, and it worked as well. So we're ready to scale up to other parts of the world. Lessons learned. So I'm trying to wrap up. What did we learn? We learned that to operationalize a foundation model, you have to be very clear about what it can do and be realistic about the expectations. So first we had some sort of marketing phrase, make monitoring in a minute. And indeed, you can train a model in a minute, but it's not done yet. And we found that people that we approached this way, they stopped giving examples after a minute. And they said, hey, I've given a single example, it doesn't work. Or there was one person who didn't give examples at all. And just pressed train model and complained that it didn't work. So, but you have to educate your users and you have to be realistic. Quality of label data is still the most important thing, right? That hasn't gone away. But what we've done is make it possible to put quality over quantity. We don't need quantity. So actually what we've done for many use cases now is throw away half of the data because it's not good enough. You can do better. If you go for a small data set that's very high quality. Maps over metrics, and this was already before we did foundation models. People keep staring at accuracy metrics, right? And we do the same, but we've learned to, in a very early stage in the use case, make maps, because you can have 10 models where the best models do slightly better on accuracy metrics. But then you look at the maps and they look rubbish. And why do they look rubbish? I cannot explain, right? There's human intelligence by looking at the map and say, hey, this looks natural, this doesn't look natural. It's a feeling, but that feeling is very important, especially for our users as well. Robustness over accuracy. We had to make a choice where if you do one use case or a handful of use cases, you can human engineer, you can tune your accuracy exactly by making a lot of choices. We don't have that freedom. We want to make something that works out of the box without us interfering, ideally. So we picked fine-tuned models that are not that sophisticated. We use support vector machines rather than neural networks. We experimented with neural networks and they score better. But you have to, they're much more finicky. They're prone to overtraining. So you have to know what you're doing, and our users don't. So that's why we pick something that is robust, that works out of the box, and maybe doesn't do as well, but it works always. And last but not least, foundation models are very hard to validate. So we validate them by training specific fine-tuned use cases. But we're trying to figure out, can we already say something about how well it is performing based on only the embeddings themselves? And that is very tricky. I think that's being figured out worldwide as we speak, how to do this consistently and trustworthy. We haven't figured it out yet. We're getting there. Then for what's next, and I'll wrap up because it's 12. Basically, two things. We're going multimodal. So not only basing ourselves on Sentinel-2, we already have a model that combines our Sentinel-2 embeddings with high-res spatial context, so that we have the best of both worlds. So on the right side, you see some experiments where we have embeddings on the 1.6 meter scale, for example, for finding solar panels, or distinguishing rows of trees from forest. So with Sentinel-2, you cannot do that, right? A tree is a tree. But if you have spatial context, you can say, hey, I don't want trees clumped together. I want them in a single row. And that works quite nicely. We can separate rows of trees from single trees from like larger areas. And after that, we have plans to expand on higher resolution time series. So we're reaching out to Planet and Airbus for their time series to see if we can work with them. Improve our temporal resolution to below the year, let's say, to have a monthly update, basically, embeddings on the month scale. And on the right side, you have interaction with human beings. And we think we should start with focusing on making the user understand the AI. So implement more accuracy metrics in Carto and help them provide with information. Have they drawn in enough observations, or is there room for improvement? Is the accuracy converging? Is it still growing? And after that, we have to focus on making sure that the AI is understanding the user. So maybe by combining a large language model with our spatial geospatial foundation model. But that's a bit more uncertain. Then my call to action, what we're looking for is basically why I'm here. It's basically two things. We would very much like scientists to use our embeddings or Carto. You're also free to use Carto, so the app around it, but start also the bare embeddings and see if it works for your use cases. So please, if you have a use case where you think, hey, this could my mouse could benefit from this, reach out, we can discuss it. And on the other side, probably 99% of masters and PhDs want to stay in science, but for those who don't, if you want to work at an exciting company, fast-growing company that has a societal mission, then reach out. We can see if there's a fit. Thanks. And sorry for taking the full hour. I hope there's some room for questions. If not, then feel free to send me an email.
So first of all, thank you very much. I think it was a very insightful presentation, giving really a kind of introduction to the topic, but also showing your use cases. That's great. There are lots of questions on the chat.
Okay.
Speaking.
Yeah.
I think we have a bit limited time, but normally for each big geodata talk, we have a event page and we have a Q&A section. So what I can promise to online participants that I will just communicate the questions to Yoko, and we will put the answers to that page so that they can find the answers there. Or if you have some time, we can just have 1 or 2 questions. But maybe first I will ask if there are any questions from the audience.
Yeah, I've got a question. Forgive me for taking that. But when you were presenting about using the temporal and you were saying you were focusing on training on the temporal dimension.
Yeah.
But then you were showing a vector that you're then using for training areas, which is then spatial.
Yeah.
I was a bit confused about how those 2 dimensions are then feeding into embedding.
Yeah, that's a very good question. Well, basically, the spatial part of it is just in your head. So I showed this a picture, and there's a spatial dimension in there. The model doesn't see it. So our foundation model trains purely on the spectral temporal data, and we are experimenting with spatial data, but for Sentinel-2 it doesn't have anything, but we are combining with other data sets where it does, like the last slide that I showed you. We use very high resolution aerial photos once a year to capture the spatial dimension, the spatial patterns, let's say, and combine it in a single embedding. But our first version, like the Sentinel-2 version, there's no spatial patterns at all. And that has a benefit because intuitively, if you look at the map and you see spatial coherence in the outcome, you know that you've done something good, that it captured something real, right? Because it cannot see the spatial patterns. So if the outcome looks coherent spatially, then it has something true.
Well, I would have many questions, but maybe one related to this, because you captured temporal features, the temporal dynamic. What is the temporal window that you're considering? Is it annual, like other foundation models?
Yeah, it is exactly the same as what the Alpha Earth and Tessera are doing. So we take a full year, calendar year of data, and we summarize that in a single embedding. Yeah.
Okay.
We're thinking about using maybe a sliding window. That's an idea that we have, or go to shorter time ranges and making sure that the foundation model can know what time of year it is. I mean, it already knows, but so we have many ideas of making the temporal frequency a bit higher, but right now it's annual. Yeah.
I was thinking applications like crop top mapping,
Yeah.
where not only the length, but when it starts and when it ends, is very important.
Yeah.
Right. So and
Funny thing there is that I think you can. I mean, the information in the embedding can be about different times of the year, right? So it might be conceivable. We didn't test it, that you can as well find the summer crop as the winter crop in these kind of embeddings, because it might just be a different part of the embedding, right? Where position 10, 20, and 21 are more looking at the winter, where other parts of the vector are looking at the spring, and that's conceivable, but we didn't test it.
Rolf?
Yeah, I have basically the same question, and I think it has been posed again here. Your examples look decidedly spatial to me.
Yeah.
They don't look temporal. Now, if you want to find out a specific crop when it is flowering, the question is temporal.
Yeah.
Or where it is flowering and where it is late flowering, etc.
Yeah.
Right now, you can't do that. I understand from your second answer, or.
No, that is true. So the refresh rate is like we have a slider on top of Carto on the top, where you can go to different years. So the refresh is like yearly, we have yearly embeddings. So you can see changes over years. Basically, you cannot see, hey, yeah. It might be possible to distinguish between, I mean, inherently, it looks at differences in growth season, right? That's why we can so accurately distinguish one type of grass in between 10 other types of grass, because it looks at the whole temporal pattern. But there's no way to use it for within year differences. No.
Yeah, following up on the spatial dimension. So it also means you can't really use the yearly events for like early morning or near real time monitoring, or how would you see?
That is true. Yeah. So right now it's not applicable. The Sentinel-2 embeddings are not, the yearly Sentinel-2 embeddings are not useful for emergency response. No. So what I imagine is that you can bring this up to, if you use a sliding window, you can make it very accurate, or at least very temporal actual. But there's always a trade-off, right? So if you make that the period you analyze shorter, then you will see a dip in accuracy, right? So it all depends on what you want to do, but I figure that will be a possibility too, especially when we have high resolution temporal data, because then the spatial information will make up for the shorter time window that you're analyzing. Yeah.
Yes.
I'll build further on the earlier questions. So if I would look at the whole of the Netherlands and look for a specific crop, then in the south it will typically germinate 2 weeks earlier than in the north.
Yeah.
And I use this data set. Can I then still find the same crop?
Yes.
Germinates at a different time.
I'm fairly sure you can, but what you will see is you might start with this crop in Groningen and be very excited about how it looks in Groningen, then scale it up to the rest of the Netherlands and think, hey, there's something off here. It's not as well behaving in Noord-Brabant. But then you can easily adjust it by training it the second iteration with some examples in Noord-Brabant. So you're right that to extrapolate it spatially, of course you will find problems, because a certain situation in Groningen will not look the same in Africa. right? Same kind of crop. So you will have to provide some local examples to make it really accurate. Yeah.
Okay. Yeah. First of all, Yoko will be with us for lunch. So maybe for the people here, I will just invite you to join us for lunch so that we can continue discussion and answer your questions. So I will take only one question from online just to take one. Basically, they say, do you sometimes find you need to combine with data that your foundation model is not trained on? If so, how do you add this?
Yes, that's actually a very good one. So I'll get back to the previous slide. So I put something on the left side, add auxiliary data. For example, AHN, which is the digital terrain model of the Netherlands. Of course, this is the case. I mean, Sentinel-2 only has so much information. There's many questions that it won't answer, right? So we're from the nature monitoring side, people have been asking for quite some time, can you combine it with a digital terrain model? And you can basically decide then to do two things. Either create a new foundation model on the combined data set, which is ultimately better, but way harder. Because then it might start to cheat. It's very hard to come up with good pre-trained tasks to get a converging model. The easier way, and that's what we're actually starting this week, is to combine it after the foundation model, just with embedding. So we calculate some human engineered metrics from the digital terrain map, and we just concatenate that on top of our embeddings. And that's what we want to do generically later on. So maybe somewhere in 2026 is make this possible for user-generated data. So have users provide data that they want to concatenate on top of our embeddings, and then train use case models on. So yes, that's indeed what you want to do. Yeah.
But this would allow time series.
It would allow time series, but you would have to, I mean, with a workaround right now, with a workaround, you can add time series, but you have to add each year separately and label it separately. So we now, our labels, because our time series are year-based, our labels are also year-based. So per label, you can say it's true in this year and true in this year, but not in this and this and this year, right? So yeah, with a workaround, and maybe sometime a bit more convenient. Yeah.
Okay. I think at one point we could stop, so maybe that's the point now. So I want to thank you again, Jacob, for this nice presentation.
Yeah, thank you for having me.
Thanks for coming. So I think it was really a nice talk. And as I mentioned, we will continue online. If you want to join, please feel free to join. Especially the invitation to collaborate, I think could be really valuable for us. So it might be really useful for thesis studies or project work. We have a lot of colleagues actually working on foundational models here, so maybe they can also provide some information what they are doing.
Can I ask one question about that? Because it's to work with you, is it also for like internships or thesis work, but also an open invitation? Or
yes, we have to be careful because we're a tiny company, right? We're 8 people with some partners as well, but we have to be very delicate with our time. So with TU Delft, we have an arrangement where indeed masters are using our embeddings or even Carto in their work, but the daily supervision is at Delft, right? And we might have them over one day a week, or but the primary supervision should be at the university. Otherwise, it's too intensive for us. Yeah.
Okay. Thank you.
Thank you again. And you at home as well.
The embedding, we should send you an email.
Yeah. So the embeddings are currently, I mean, they're not